Hello and welcome to this clip on acids, bases and salts. What we'll look at first of all is the common acid-base reactions you need to know, and then look at how to define to a high-level standard what an acid, a base and a salt actually is. Then we'll look at how to identify the acid, the base and the salt in a reaction, and how to write out these reactions as ionic equations so you can easily see which ions are reacting and which ions are the spectator ions. It'll be assumed throughout this clip that you have a working knowledge of the common ions in A-level chemistry, so having your ions list handy would be really useful. So there's some standard reactions that you need to be able to memorise and commit to memory so that you can apply them to any pairing of an acid with either a metal oxide, a metal hydroxide or a metal carbonate. So these three standard reactions are examples of acid-base reactions, and they're all classified as neutralisation reactions. So an acid is a substance which releases hydrogen ions, otherwise known as protons, or H+, in aqueous solution. A base will absorb these protons, and during neutralisation, a base and an acid will react together to make a salt. The acid by releasing the H+ ions, and the base by absorbing them. When I say absorbing, it will obviously be reacting with them. So you also need to make sure that you are familiar and confident about the difference between an acid, a base, and an alkali. And a common misconception that creeps in at this point sometimes is that people think that all bases must be alkalis. Not true. All alkalis are bases, but not all bases are alkalis. These are the common examples that you've probably heard about already. They're strong acids that give off H+ readily by fully dissociating water, or strong alkalis that again fully dissociate in water to give OH-. And these would be the equations you'd use to write out these dissociations. Something to watch out for is the mole ratios. If you have an acid that has 2 hydrogens in it, watch out because it might actually give 2 H+ for every 1 acid. Likewise, if you've got a base or an alkali which has 2 OHs, it'll get 2 OH- for every 1 alkali. So something to watch out for there in terms of mole ratios. So in general, acids will be seen to release H+, and alkalis will be seen to release OH- in aqueous solution. So let's look at a neutralisation reaction. What's actually really going on? If we take everything that's aqueous and we split it into the ions that it's made of, you can see clearly that some things actually appear twice. And we can cancel them out. So we've got H+ reacting with OH- to make H2O. If we do the same thing with one of the other combinations, you'll see actually we end up with the same reaction. Again, H+ and OH- reacting to make H2O. No surprises, it happens a third time with the other combination. So what's with this H+ and OH- giving you H2O? So that gives us, in all acid-base reactions, we get the standard ionic equation for neutralisation, H+ plus OH- giving you H2O. So this happens every time an acid and an alkali react. So let's look at a couple of examples that include other bases which aren't actually alkalis. We looked at acids and metal oxides. We looked at acids and metal carbonates and gave their standard reactions. I've given a couple of examples, one of each. So just like I did before, I've split all of the aqueous compounds into their ions. And I cancel what appears on both sides, and I get the standard ionic equation for when an acid and a metal oxide react with each other. Why not pause the video and see if you can work out the equivalent one for an acid and a metal carbonate. Hopefully you were able to split everything that's aqueous into its ions. If you did so, well done for getting that. Now what we have to do is to cancel what appears twice. So you've guessed it, it's the sulfate, it's the sodium, which leaves us with our ionic equation. So ionic equations are a useful way of showing exactly what ions react and what ions don't. So the ions that don't react, the ones that are crossed out in other words, are called spectator ions. And take note also of how I've split the base into its ions anyway, even though it comes as a solid. So the base in each case is calcium oxide and sodium carbonate. The reason I've split it into its ions is because on contact with acid in aqueous solution it'll automatically dissolve. As it dissolves, it'll split into its ions naturally. So even though it's listed as a solid, because that's how it comes, and you add the solid to the acid, the solid then dissolves, and as it does so, it splits into its ions. So therefore that's why I put Ca2 plus and O2 minus for calcium oxide, and 2Na plus and CO3 2 minus for sodium carbonate. It's a good one to watch out for there, because they do sometimes list it like that, and you're expected to know that as a base, as a solid base, it would dissolve naturally in an acid. So looking at the reactions from the last slide, let's apply the idea of what a salt is to those same reactions. So a salt forms when hydrogen in an acid is replaced by a positive metal ion, or NH4+. So in the first reaction you can see that H plus in HCl has been replaced by Ca2 plus to make calcium chloride. And in the second reaction, so it's worth also remembering from GCSE which acids form which salts. Hydrochloric acid will always form chlorides, sulfuric acid will always form sulfates, and nitric acid will always form nitrates. So let's take a moment to look at ammonia. This is a gas at room temperature which dissolves readily in water due to intermolecular forces such as hydrogen bonding. And when it actually dissolves in water, it does more than dissolve, it actually reacts with water according to this equation, producing a compound called ammonium hydroxide, which dissociates in water into the ammonium ion and the hydroxide ion. And the thing about the ammonium ion is it can do exactly the same thing as metal ions can do in acid-base reactions. It can replace hydrogen ions in an acid to make a salt. So you can see that in this example of ammonium hydroxide reacting with nitric acid to make ammonium nitrate and water. And you can see that this is also a neutralisation reaction. Let's split the ionic compounds in aqueous solution up into their constituent ions and get an ionic equation. So you can see clearly that the NH4 plus has replaced H plus in HNO3 to form ammonium nitrate, or NH4NO3. So if I was to highlight the nitrate ions, you can see that H plus is gone on the right hand side of the equation and we've got NH4 plus instead. And we have the same ionic equation as we had before for other neutralisation reactions. So in this way, ammonia reacts with water to produce ammonium hydroxide, which goes on to behave as a base and neutralise an acid and replaces the hydrogen ions in the acid with NH4 plus ions instead, forming the salt, in this case ammonium nitrate. And it's a neutralisation because H plus and OH minus react with each other to make water in the ionic equation. Right, so there's a few exercises for you to try now. What I'd like you to do is pause the video clip and see for each of these reactions if you can write out the fully balanced equation, the simplest ionic equation, work out whether it's a neutralisation or not, and if it is a neutralisation, which substance is the acid, the base, or the salt. So this should take you about 5 or 10 minutes to do. It pulls in all the stuff that we've done in this video clip, and it also pulls in the skill of being able to construct formulae from ions. that you would have done earlier on in your course. So grab a piece of paper and see if you can do this. If you can do it without the assistance of your ions list, all the better. So these are the balanced symbol equations. Notice that there's two possible ways you could deal with the idea of aqueous ammonia. Aqueous ammonia could simply be NH3 in aqueous solution, or it could be NH3 reacting with water whilst in aqueous solution to produce NH4OH. So either of those two are acceptable. So there you have the individual full ionic equations for each reaction, including the two possible options for ammonia, or aqueous ammonia. In the boxes you've got whether it's a neutralisation or not. Obviously the first one is not a neutralisation because the magnesium metal is not behaving as a base. This is a different type of reaction that we'll come across in due course. If you've done reduction and oxidation, you'll know it's a redox reaction, but like I said, that's beyond the scope of this clip, so we'll cover that in a different video clip. The second reaction, aluminium carbonate and hydrochloric acid, you'd have done well to get the full balanced equation because that's a slightly tricky one because of the mole ratios required, based around Al2CO3 requiring multiples of everything else. But the ionic equation for that is the same one we looked at before for the reaction of carbonate ions with H+. So for aqueous ammonia, you can see I'm treating it in two different ways. The first one is where I'm taking it to be ammonia gas being bubbled through aqueous hydrochloric acid. So NH3 is a gas reacting with H+ in aqueous solution to make NH4+ in aqueous solution. And the second way I'm dealing with aqueous ammonia is that it's NH4+ and OH- already in aqueous solution. So therefore the ionic equation will give you OH- aqueous plus H+ aqueous, giving you H2O. So two slightly different ionic equations for essentially the same thing, being treated in two slightly different ways. So hopefully this clip was a fairly useful introduction to how we do acid and base equations and how we do ionic equations as well. If you've got any queries, do jot them down and bring them in to your teacher, or maybe come and see one of us in a subject extension at college. In the meantime, thank you for your time and see you soon.